Okay.
So let's continue with where we left off. You guys see my whiteboard here?
Yeah, we can see it.
Okay, any questions on anything before I dive in? I was able to post another set of homework problems. And these homework problems are more computational than previous ones. So you'll be writing some code in order to solve the problem. So you should take a look at that. We still have to get through the material, but at least it's there for you to begin to start thinking about. Any other questions on anything? Okay, so let's begin. Where we left off was we had derived the weak form for our elastic bar problem. And it looked like this, just to remind us. Let me write it down. That's dx plus 0 and 0. That was our first equation in terms of variations of the displacement u, and then we had one for the Lagrange multiplier. Which was just a very simple equation because of the 1D nature of our problem. Let's see. Okay, so there's our weak form. Now, what we want to do next is derive the strong form. And really the question is, why? Like, who cares? Does anybody know off chance why we derive the strong form, also known as the Euler-Lagrange equations? Like, why we would care about this? Anybody familiar enough with this to venture a guess?
Is it so that we can do like a check to make sure we're getting the right solution?
Yeah, so that's basically right. So what we do with the weak form when we turn it into the strong form is it tells us exactly what the equations are that we're solving.
It's like a validation step.
Well, it tells you, like, point-wise, if everything is smooth enough, it'll tell you, like, at every point exactly what the equations are that you're solving. Whereas the weak form just tells you under the integral what the equations are. And so it's kind of hard to deduce exactly what the equations are. So let's go through this and then you'll see what I mean. Yeah, so it's kind of what equations we are solving. And that will be clear once we go through this exercise. So what do? To get the Euler-Lagrange equations, basically you use integration by parts to remove any derivatives from these delta quantities. These are called test functions. Everything with a delta is called a test function. And we want to have all the test functions, they shouldn't be differentiated. We want to remove the differentiation from all the test functions. In this case, there's only one place where a test function is differentiated, and that's up here in the strain energy term. Everything else will remain unchanged. So we're going to use integration by parts on this first integral in order to get rid of this derivative. So let's work on that down here. So we use integration by parts. Okay, so let's just take a look at the integrand. So we have delta u comma x EA u comma x. Remember, just from the product rule of differentiation, that delta u EA u comma x, and then if we take that whole thing and differentiate it, then we have a product of two terms. That's going to be equal to delta u comma x EA u comma x plus delta u EA u comma x x. Notice our integrand right here is actually this guy. So we can subtract this over to the other side, and that gives us integration by parts. So this guy right here is going to be equal to delta u EA. And notice there's no differentiation now on the test function. X minus delta u EA u comma x x, and then let's just go ahead and integrate these guys. So that is integration by parts. It's just the product rule of differentiation rearranged. Okay, so now we have two terms. Both we've been able to successfully remove the derivative. This guy, we can now just use the basically fundamental theorem of calculus, and we can differentiate it directly. So this is going to be equal to delta u EA u comma x evaluated from 0 to L minus 0 to L delta u EA u comma x x dx. All right, and then our last step is we've got delta u evaluated at 0 EA u comma x evaluated at 0 minus delta u evaluated at L EA u comma x evaluated at L minus this term here. So that's what we did just to this first guy to get rid of this derivative. Now let's rewrite everything now. Let's come up here and replace this with these two terms, these three terms, and then collect terms. And you'll see that these equations will just start to pop out. So let me go ahead and erase this. Okay, I'm going to move that up. Now, delta u minus the integral 0 to L delta u EA u comma x x e x. plus these other terms. All right, great. So let's collect terms now. And once we collect terms, the strong form or the Euler-Lagrange equations will pop right out magically here.
Mike, do you have the sign wrong on those first two terms you just put up there?
I don't think so.
I thought it was evaluated at L minus evaluated at 0.
Oh, I did them backwards.
Yeah, that's, I was wondering that as well.
Thank you, guys. Yeah, I did them backwards.
Thank you for speaking up.
Yeah, please, yeah, you make mistakes when you're talking and writing at the same time. Okay, so let's gather up these guys and look at the equations. So you notice, you know, kind of implicit in this this integration by parts is we're assuming that U makes sense with two derivatives. Okay, so there's kind of an implicit assumption that if everything is smooth enough, you can do this. Okay, that's kind of a classical assumption here. So now what we want to do is we want to gather everything that's written in terms of delta U0, everything that's written in terms of delta UL, and everything that's written in terms of delta U, and combine them into their own equations. So let's start with delta U0. We have this term here. I'll get a different color. So delta U0, we've got this guy here, and this guy here. Okay, so let's write those. We have delta U0, and then we've got lambda, which is our Lagrange multiplier, minus EA, U comma X at 0. Okay, there's our first, this is our first equation right in here. I'll explain why in a minute. Now let's gather up all the delta UL guys. Look at these right here. So we've got plus delta U at L. And we've got EA U comma X evaluated at L minus the traction. Okay, so those guys are done. We've got this guy, this guy, this guy, and this guy. Now let's gather up the delta U terms. So what do we have here? Got a sign off here, maybe. Let's see. Let's see, we got an integral. Let's just do this delta U. And then we've got got a sign off here. It's not going to matter. F. Okay, so there's all of those guys, and then let's quickly do this last one, which we don't have to do anything because there's only one equation. Okay, so now why do these, what does this tell us? The reason this is valuable is because notice that the weak form, these d pi's up here, they have to hold for every test function, whether it be just a test Lagrange multiplier or a test displacement. So if these guys can be non-zero, and then remember, this whole thing has to be equal to 0, right? So this whole thing has to be equal to 0 for every possible function and number that you can think of. So if that's the case, then one of them is going to be a non-zero guy. So if this is non-zero, then the only way this can be 0 is what? If this equation is 0. Okay? And same, you can make the same argument for all three of these guys. Because this has to hold for every possible test function, the only way that this whole equation can be 0 is if the things in the brackets themselves are equal to 0. So that gives us a couple of equations. It gives us that E A u comma x x plus f is equal to 0 in the domain 0 to L. That's what this guy gives us. This guy over here says that E A u comma x evaluated at L has to be equal to H sub L on at x equal to L.
Why couldn't those terms be like equal to each other? And then they cancel each other out.
Because it has to hold for every single possible test function. So there will be times when like the test functions will be different values. You can't equal it. Okay, then that one's done.
This is what it is when it's true everywhere.
Exactly. That's the point. That's the trick. E A u comma x at 0 at x equal to 0. That's this guy. And then we've got this equation right here, which says exactly what we should expect, that our constraint is satisfied. Okay, so these right here, we've got our Euler-Lagrange equations. Let's manipulate them a little bit just so that I can convince you. Anybody who has been through an engineering curriculum, an undergraduate engineering curriculum, has studied these equations extensively. So let's manipulate them just a little bit so that you're convinced of this. Okay. So the equations that are satisfied, let's kind of pull these up and rewrite them a little bit. This right here, let's not worry about, let's just pull f over. It can be negative f, positive f, doesn't really matter. That negative can be eaten up by f. So we have A E u comma x, assuming that these guys are constant, is equal to f. Just assume it eats up the negative. 0 to L. Will somebody tell me in 1D what Young's modulus times u comma x is? What do we call that?
Stress.
Stress. This is the Cauchy stress in 1D. This is the strain epsilon, u comma x multiplied times Young's modulus. So we have A, maybe I won't make such a big jump there. So we make, so we've got A stress comma x is equal to f. The A can come out because it's a constant, and then we divide by A. And we get our very famous equation from beginning strength of materials that says this. Okay, so what this is saying is the rate of change of stress is going to be equal to basically the body force, which I wrote as a capital for some reason. Okay. Little f, which is a function of x. And that makes sense, right? The rate of change of your stress should be equal to the body force divided by the area. Okay, so this is actually in 1D, this is a one-dimensional statement of conservation of linear momentum. And another way to think about this is, if you've seen this before, is this the divergence of the stress is equal to F, is what this is. If you were in multi-D, this is what this equation would be. And some of you have probably seen this more general equation. That's what this is in 1D. Okay, so let's rewrite that up top now. Okay, so our weak form that came from our strain energy kind of miraculously is enforcing conservation of linear momentum. That's pretty cool. We have sigma comma x is equal to f over a on the domain 0 to L. So that guy's done. Let's do the same trick here. This is the traction at x equal to L. Again, you see the strain here times Young's modulus. So this is again sigma evaluated at L better be equal to the traction divided by the area. That shouldn't be a surprise to anybody. Okay, so if you evaluate the stress at the right endpoint, it better be equal to the applied traction force divided by the area, right? And then we've got that, now we're gonna get like our definition of our Lagrange multiplier, which is that lambda, the Lagrange multiplier, what it really is nothing more than, let me write this in there. Sigma evaluated at 0 is equal to lambda 0 divided by a at x equal to 0. And then finally, we have our displacement constraint, u at 0 is equal to u naught at x equal to 0. Okay, so now I hope you can see why, like, it's not, even in 1D, like, unless you kind of knew the answer ahead of time, you wouldn't be able to really look at either the strain energy equation or the weak form and just automatically deduce that these are the 4 equations that are satisfied. And so we call this the strong form. And I hope you see from elementary strength of materials, do you see what's happened here? It's nothing more than a bar in tension, right? This is just like what you learned at the very beginning of your first undergraduate strength of materials. Now, the Lagrange multiplier, of course, you didn't see at undergraduate level, but how do you interpret now the Lagrange multiplier? What is it? Does anybody care to interpret what this Lagrange multiplier is just by looking at this equation?
Body force function F.
I would call it the boundary condition.
Yeah,
Oh, I
so
misunderstood the question.
what is, like, tell me what lambda is. I mean, this equation tells you exactly what lambda, how you interpret the Lagrange multiplier. So you've got, remember, stress is some force over area, right? So here's stress, here's the area, so what must lambda be? It must be a force. And in fact, it is a force. What is this force here?
The reaction force?
Exactly. It is the force. This lambda is the force required to make sure that this constraint is satisfied. Right? So you take the end of the bar, let's say, and you displace it some u naught. And as you displace it, right, there's going to be an internal force that develops inside the bar. That's what this is here, this lambda. So lambda, the physical interpretation of the Lagrange multiplier, can be deduced from the strong form. And it says that lambda is nothing more than the force required, can be viewed like a traction force required to make sure that this displacement constraint is satisfied. Okay, any comments or questions about this? This is a very, so no matter how complicated your method is, this is the way we do it. The way you should do it is you go through the weak form and then you deduce the strong form or vice versa, because now I know I have a real physical handle on what my method is doing. I know that if I refine my mesh enough, then this guy right here is, these equations are going to be satisfied. Okay, comments, questions?
Can you always get a strong form, or is it like at times it's kind of numerically impossible?
The strong form assumes you have an infinite number of test functions. So your finite element method, though, these are the equations that it's going to be trying to approximate. You can always derive a strong form from a weak form, but remember, in the weak, we haven't discretized yet. We're still in the infinite dimensional setting. So your method, once you discretize, is going to be approximating these equations, these strong form equations. Okay, any other comments or questions?
I have one.
Okay.
So the top one is the derivative of the stress equals force divided by area, right?
Mm-hmm. Yeah.
And then below that, just the plain stress at a place like L is
Mhm.
equal to the traction
Mhm.
divided by A.
Yep.
Is traction the same thing as force?
Yeah. So this is a body. So because I teach introductory strength of materials, I know kind of what you're trying to pin this on in terms of like your intuition. This is called a body force. Okay. This guy right here is the force you normally see in strength of materials. So normally in strength of materials, we assume that the body force is 0. Okay, now look what happens if the body force is 0. Then all of a sudden you know something more about your equation. And this is why they do it in introductory. If this is 0, what do you know about your stress?
Constant.
Yep. So if there's no body force, then the stress is constant. And then what do you know about your strain?
It's constant as well.
It's constant as well. And so in introductory strength of materials, this is actually the strong form that you study without all the Lagrange multipliers, right? You have a beam, you have some bar, you fix it on this end, which means U naught is equal to 0. So then all this goes away here. And then you apply H sub L. Often the strength of material text will call this P, P over A. The classic sigma is equal to F over A or P over A or whatever. But that is nothing more than this more general equation where you've assumed that there's no body force being applied to the beam.
So I think a follow-on question, and maybe this is what Rebecca was getting at, is the units for F and H must be different, correct? So they're not both really a force, right? What's the difference between a traction?
Yeah, so can anybody look at these equations and tell me what the body force better be? The units for the body force?
Maybe undo the changes you did to the equation.
It should be per volume unit.
Yeah, so in general, body force is always like force per volume, but this is a 1D problem, so volume is just a line. So the so this guy right here is going to be some force per length. That's the units of this guy. Okay. And H is going to be units of just force. Lambda is going to be units of force. And then this is just units of length. So if you plug in, you know, force per length, you get a force per volume, which is what you should expect in general, right, for the stress. So stress, the derivative of the stress is going to give you units of force per volume.
Thank you.
And in the course notes, I go through it in detail, all the different units. Okay. All right, good. So that's encouraging. So that's the problem we're trying to solve. Let's move on to the next thing we want to do here.
Dr. Scott, I have a quick question.
Sure.
So before, like, I believe last class, we were talking about what U has to be inside of. We mentioned it has to be inside of H1 because there's not only constraint on U itself, but on the derivative. So in deriving the strong form, we took the second derivative. Does that mean that it actually has to be inside of H2 in that case?
Yeah, and in fact, the classical, if you notice that here, this is actually, there's a second derivative on U and it has to hold pointwise. So in fact, it has to be even stronger than H2. It has to be in a C2 space.
Okay.
That's why it's called strong. They're stronger equations. And so they only hold for certain levels of differentiability, which is why we go to the weak form.
Okay.
Yeah.
Thank you.
Okay, so now let's talk about discretization. Okay, so here's where we're going to introduce a new method. So we call this method the, let's see, flex representation method. The acronym is FRM. And let me give an example of where this comes from. So in our little elastic bar, remember, it's defined from 0 to L. So our problem domain goes from 0 to L. We call this domain omega C. And the superscript C is going to stand for CAD. So in 1D, this is pretty trivial. But in multi-D, we're assuming that our domain of our problem is defined in some kind of computer-aided design. Okay. Now, so our problem is posed over omega C, but we're going to introduce a discretization in terms of another domain. Let's assume that I've offset them, but it's on the same axis, right? This is both the X, these are both on the X-axis. Okay, and we're going to call this maybe just the left endpoint, superscript F, and the right endpoint, superscript F, and we're going to call this domain omega F, and we'll call this a flex domain. And notice that the only requirement that we're going to make on the relationship between omega C and omega F is that omega C has to be contained in omega F. So omega F and omega C could be the same domain, right? So we could set the left endpoint to 0 and the right endpoint to L. That's one option. Or we could set the left endpoint to 0 and the right endpoint to L plus some epsilon, some value. That's why we use the term flex, because we're going to solve our finite element problem on this domain, but our physical problem is going to be posed over this domain. And that's going to give us great flexibility that is optimal for splines. You see, you never really did this in traditional methods. Normally, these two domains are on top of each other, With lower order finite elements, that's a good way to do it. With splines, you don't actually need that constraint because of the power, the approximability of these spline representations we're going to be using in this class. Okay, so so this is another kind of exercise in notation here we have to go through. Let's see. Yeah, let's add some more notation in here. So we're calling this guy here is our gamma D in the CAD. So the superscript C is always going to indicate the domain that it comes from. And then the subscript gives you some additional information. So this is saying that it's the boundary associated with displacement constraints, which is why we have the subscript D. And then this guy is gamma. Gamma HC. In this case, it's just a single value, right? L. In this case, it's a single value 0. And this guy is 0 to L. And then we've got our body force. This is, we're applying U naught right here, our prescribed displacement. We're applying our prescribed traction here. And then we've got our body force F of X being applied there. Okay, and feel free to stop me here. Yeah, I mean, this is going to be, we're going to be digesting some notation here, so please stop me. All right, now what we're going to do is, remember, we need to go to a Galerkin form here. If you remember from before, we make a Galerkin approximation. Which means we approximate U with something called UH, and we'll approximate lambda at 0 with something called lambda at 0 superscript H. And these guys have to be written in terms of some basis, right? Because this is discrete now, finite. So let's pick a basis, this guy. U, H, let's write this basis here. U, H. Going to be equal to some coefficients times some basis. So these are our basis functions. Okay, now here's a big point. These basis functions, these NAs, they're going to be defined here, not in the actual domain of our problem. We're going to generate a much more flexible way to do discretization by just putting our basis functions on this larger domain that just has to encapsulate the domain of our actual problem. And that's where the term flex comes from. It's a more flexible way to discretize with splines. Okay, so let me draw a picture now so that you can just at least pictorially see how this is done. Okay, any questions on what I've got so far?
Dr. Scott, you said because of the flexibility of time, we can do this. So do you mean that we cannot do flex if we are using just linear elements?
You can. So this method will You can do that, but the accuracy will be such that you wouldn't want to do it this way.
Okay.
So there are specific properties that we're going to be leveraging that give us this. We're going to be trying to expose this additional flexibility because of the fact we're going to be using splines. Okay, let's draw some more pictures. Was there another question?
Yes. The body force F of X, is that like gravity, or does that come from attraction?
No, it's something separate. It would be like gravity.
Okay, that
So
makes
think
sense.
of body forces like gravity and tractions like a pressure.
Awesome.
All right. All right, so let's take a look now at how we're going to do this. So we've got our, let's call this our omega F. Okay, remember omega C lives inside of omega F somewhere, but we're not going to worry about that for right now. Let's just focus on omega F. And the way that we're going to build omega F is we're going to generate a change of coordinates function. We'll call it big X F. And it's going to take some, what we call parametric domain. And we'll use these hats to denote parametric domain. So this is what we call the flex parametric domain. And this guy is more aptly named the flex physical domain. It's a common term. So physical coordinates are the coordinates that we're actually interested in our simulation. Parametric coordinates are the ones that we're going to use to make it easy to build the physical domain. So this mapping XF is going to take this omega hat F into the physical domain. Okay, now we're going to build our basis functions here. So we're going to take the parametric domain and we're going to discretize it, meaning let's chop it up into elements. So we'll call each of these little subdomains here an element. We'll denote it like this. Okay, so this is called an element. It's nothing more than a subdomain of our parametric space. And now we're going to take these elements and we're going to build a basis function over this line here that's been chopped up into elements. And what we're going to do is we're going to build what are called splines. Okay, so we're going to build splines over each element. So the difference between what you learned previously and now is that a spline is a piecewise polynomial. So everything you've learned up to now is basically you have been studying a single element, right? We had a single domain, we built a little set of basis functions over that single domain, and then if we wanted more functions, we increased the degree of the polynomial basis. Splines, what they do is they say, okay, I'm going to build polynomials over every single one of these elements, and then I'm going to connect them together across the element boundaries with some level of smoothness. Why might we want to do that? Why might that be a good idea? anybody has experience with splines or just intuitively, why might we want to move away from a single element with increasing degree to a multi-element setting where we can fix the degree but subdivide into more and more elements? Why might that be a positive?
Adaptivity.
Say that again.
Adaptivity.
Okay, what is that word? What do you mean by that?
Well, being able to resolve something inside of your element without needing to do extra stuff.
But can't we do that with a single element by just increasing the degree? Can't we increase the number of functions by increasing the degree?
Yeah, but it's not as complete a solution space.
But can't you approximate any function with a sequence of polynomials? That was the very first thing we learned. I don't mean to be picking on you, Curtis. This is an important point.
No, it's okay. Pick on me. I mean, I remember seeing in the early papers on this stuff, people stating clearly that it would not work without splines.
Oh, that's what I'm asking, is what about splines is valuable?
I don't know, but I know that
if I wanted 10 million functions, I could make a 10 million and 1 degree polynomial space over a single element, couldn't I?
Would
but
part
it's
of the
not
key
as
being
stable, right?
piecewise?
Okay, well, somebody else was talking in the background. What was that? Was that Clint maybe that was?
Oh, sorry about that. I was just saying, could it have something to do with the fact that splines are piecewise? So it gives you more flexibility, and then you can increase the degree of the polynomial, but the fact that it's piecewise allows you to broaden your reach a little bit.
Okay. You guys are getting close. What's the problem? There's a homework problem. What happened when you increase the degree to the conditioning of the mass matrix that you were, for those of you who've done it?
Oh, okay.
And the condition number get a lot higher.
Yeah, the condition number grows and grows and grows and grows. And so numerically, so theoretically, sure, we should be able to do everything with a single element, right? Just put like really high degree polynomials over it. But the problem is that those polynomials are subject to Runge's phenomena, first of all. And the conditioning is also poor as you go up in the degree. So what a spline does is it says, well, let's fix the degree. Maybe we pick degree 3 for each element. Okay, and so on. And then we say, okay, I'm going to fix what I call K. So let's say, so P indicates the degree of the element basis, polynomial basis. And then let's call K the smoothness or differentiability across element boundaries. Okay, so maybe K, for example, is going to be like at the endpoint, let's just make it discontinuous. So it's -1. Maybe we make it C2, 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 C1, C0. Okay, so what you're doing is you're connecting one polynomial segment to its neighbor with a certain level of smoothness across the boundary. And what that allows you to do is you can fix the polynomial degree, but notice you're adding functions because you have multiple elements. So this is a much more stable way to increase the size of the space because it keeps the polynomial's degree at a same level, and then you can use smoothness to begin to approximate these higher order functions across element boundaries. And so that's why splines, for example, aren't subject to nearly the Runge phenomena that you would see with higher order polynomials because of this type of construction. And same thing with finite elements. We like splines because of this reason. Traditional finite elements use p equals 1, and then they're just, the k that they use is equal to 0, so it's just C0. We're going to use higher order polynomials with higher order smoothness and leverage those properties in this flex method to enable us to like overcome the constraints of having the CAD domain and the discretization domain having to match, which is one of the big problems with finite element methods today. So I'll continue on, well, we'll do a recitation on Friday. If we have time after questions, I'll continue on Friday. Otherwise, we'll pick this up on Monday and we'll finish out this definition of splines through what's called Bezier extraction. And then we'll go ahead and discretize our Galerkin form and generate the matrix equations that you can type into a computer. So let's stop there. So I'll stop the lecture now, but I can hang around for a little bit. And Kaylin, once everybody drops off, you just hang on. We'll talk for a little bit after.
Sounds good.
So I'm open to any questions.
Quick question: when you go from omega c to omega f, do you have to do a transition of or a change of variable, or do you have to do some sort of transition to that step and then do another step to omega hat of f?
Nope. No, in the physical coordinates, these omega c and omega f are both written in terms of the same coordinate system. Just
okay.
The physical
It's
system.
just omega f is larger.
That's exactly right. Yep.
Okay.
What you're going to see is that, in fact, so like let's say omega c maybe is let me get a little red guy here. So maybe omega c is like this, right?
Mm-hmm.
There is going to be some parametrization. Let's call it big X of c, but we're not even going to need to know about this. And this is where the flexibility comes in. The CAD, all we're going to need to know is its position in physical coordinates. We're not going to need to know how it's parametrized.
Okay.
Which is a big deal. Yeah.
Dr. Scott, so you said that the Runge's phenomena isn't a problem for splines, but is it because of,
it's not as much a problem?
Yeah, so is it because of splines, or is it because that we are not doing interpolation here? Because the control points are not really interpolation nodes, because if we use splines like we do in beams with C1 continuity, we get Runge's phenomenon there, right? Because we are doing interpolation.
So I know for a fact that there's a lot less, even if you interpolate with splines. So if you generate an interpolating spline, you'll have less Runge's phenomena than just a higher order polynomial. Okay. And the reason is because you just have a bunch of segments of low order polynomials. So they can still be, each individual segment, you can still see some Runge phenomena, but the point is that you've enriched the space without increasing the degree. Even in polynomials, you really only see it for high degree polynomial spaces. So the fact that you can keep the degree low is an important part of why you can suppress that behavior somewhat.
Okay.
Mike, this is Carl.
Yeah, hi, Carl.
So I just want to clarify something in my own brain. Okay. So typically, in a typical finite element world, we could do either H refinement or P refinement. H refinement basically means let's just add a bunch more elements. And P refinement, we're going to add a higher degree.
Correct.
So you're saying that the problem with the P refinement, I need to go through and do that homework assignment, is that as we increase the order, we're actually reducing the condition number of the matrix. and our error then, our numerical error then increases.
Yep. So they're just ill-conditioned. High order polynomials are ill-conditioned. And so in the previous, I mean, they suffer from this oscillating phenomena called Runge's phenomena. They're ill-conditioned. They're it's hard to generate stable algorithms for them. There's a lot of reasons why, but the fundamental thing is the conditioning of the space deteriorates. It's like trying to fit a whole bunch of functions over one domain. Eventually, they all start to look like each other. And so that's where the ill conditioning comes from. Whereas if you chop it up into like a bunch of elements, one function ends and then another one begins, right? And so they're kind of separated. And so that improves the conditioning.
Interesting. So there was a company called RASNA, probably 20 years ago at least.
Yeah.
And their big claim to fame was, well, they could do this with higher order polynomials.
Yeah, and the problem, and we're going to show in the next lecture, so there's that, and then we're going to look at the spectral properties of splines, and there you can see why RASNA failed.
Okay, interesting.
Yeah, so there's like a really, even in 1D, we will go through it. So in this sense, you've got H adaptivity, you've got P adaptivity, but now you also have K adaptivity, which is you can change the smoothness, and this is the important one here. So,
and Mike, speaking of higher degree, is that getting into the territory of MFEM techniques? I know it's kind of a small little niche, but if you could give.
So they use spectral elements. Spectral elements is another word for basically a big macro element with really high order functions on it. They use polynomials. Sometimes they use like other analytic functions like sines and cosines. But yeah, there are certain phenomena where you can do spectral element methods really well. Another big thing, which I haven't gotten into in the lecture, is that geometry, remember, we have a line here. Our geometry is a line, so it's not very exciting. But for complicated geometry, it's not smooth everywhere. And so remember, if you have a single element, these polynomials, they're actually C infinity on the inside of the element. So if you're trying to map a million C infinity polynomials onto some CAD geometry that has, you know, a bunch of features on it, every single one of these features you're going to see Runge's phenomena. Okay, and so another nice thing about finite elements is because you keep the degree low and you have these abrupt changes in continuity, you can use that to fit complicated CAD models really well. And that's another reason that we like low order finite elements is, in fact, the element decomposition is leveraged in order to fit complicated objects. Whereas spectral elements usually are used on things like maybe fluid mechanics, where you're just looking at fluid flow through like a box, right? There's very little, you don't see a lot of geometry in spectral methods. Yeah, these are good questions.
Mike, may I ask you a question?
Mm-hmm.
So during your lecture, I referred to some of the early papers on immersed, and what I had in mind is, I recall being left with the impression at one point that people were having an issue if they used, if they were using, you know, shape functions that were not splines, that when they rotated their geometry inside of their immersed grid, they would get a slightly different solution. Was that strictly from numerical error due to conditioning, or is there something else going on there?
If you've got a, so if you've got a spline basis that's positive and satisfies a partition of unity, it has what's called a fine covariance. it'll satisfy what's called affine covariance. What affine covariance means is that you can take the nodes and apply any kind of linear transformation to the nodes, and the geometry will also respect that same transformation. So what you're describing, what I think I hear you saying is that you rotate it and then the geometry changes. That's because the basis doesn't satisfy this property. So all good spline bases satisfy this property. That's why it's used in CAD so much. So you're never going to see that.
In the case I'm thinking of, the geometry was the same. It was just rotated in its immersed grid.
Oh, okay. Oh, I see. Yeah, then that's just numerical error in terms of, yeah, because they're, depending on how you're doing the cut cells and all of that, you're going to get error depending on how the geometry is embedded. Yeah, and so that's.
So it was. Go ahead.
Yeah, so that's why we like to use higher order methods, smooth methods for these embeddings, is that the game we're playing here is, can you overcome mesh generation and still beat the pants off of lower order finite elements? That's the game we're playing here.
So they could still solve their problems, but they were just getting a ton of error.
Yeah, I mean, normally, you see, normally what I'm proposing here in 1D is all that I require is that the CAD be embedded in this flex domain. In immersed, they actually have an additional constraint that they imply. They also require that this thing be some kind of a rectilinear grid. I'm not requiring that. This domain can be any spline representation. It can be as complicated as omega c. And so what you can do is you can tailor immersions that are really accurate if you mimic the parameterization of omega c. This is like the worst possible way to mimic. Like you put like some complicated object in here and then try and get it to conform to a rectilinear grid. That's going to be tough. That's not what we're doing. You can do that. That's one sub method, but we're going beyond that.
Is there literature written on that?
On what?
On having this super complex immersed grid that isn't rectilinear.
Yeah, I'm writing it on these during class.
Okay, good. I'm happy to be on the front lines of that.
This is what the graduate classes are for, right? Yeah, this is basically what I'm trying to expose you to is like, this is where the field is going, right? Not where the field has been.
Sure, I don't think I've ever seen anyone not use a rectilinear spline grid.
Yeah, it's the worst idea in my opinion. Like what we're going to show is that you can get like orders of magnitude improvement in solution behavior just by tailoring your immersion a little bit better. It's still just as easy to build, but you have to have these higher order mappings. And then the inversion of these mappings becomes important, which is one reason why nobody's done it, is because you have to have very advanced geometrics, like spatial reasoning algorithms to figure out how to invert the mappings.
Well, Mike, I wish I'd have had my camera on so you could see my draw drop. I think you would have appreciated it.
Your jaw just dropped. Okay. All right.
Yeah, I was shocked by your statement, so it's cool.
Yeah. Yeah. After a while, your graduate courses are one of the ways that you keep learning stuff. So, yeah. So I try and keep changing them up a little bit. Okay. Any other questions? All right, let's stop there. Let's have everybody go.